Due to our setup, Shelby Kane, I will have to be using DJ's mic so that we can present fluently. But this is our North Greene High School Moon 101 presentation with DJ, Laura, Gabby, Shelby Kane, and Jada. Thank you.
Our first Moon 101 image. In our first Moon 101 image, the craters in this image appear to be elevated and there are no lava tubes present. The large crater in the upper right-hand corner appears to have a few small craters inside of it, and this led us to believe that it was older than the smaller craters surrounding it. There are also some small craters with very clear and defined edges that are younger than some of the other softer appearing craters. And this image seems to be a part of the Lunar Orbiter Mission 5 photo gallery. Next slide, please.
As you can see in the red circles is the older craters. And in the white circles are the newer craters. You can see it's like the ones in the red are like more fainted and they've been like built up with dust and stuff compared to the ones in the white circles. Next slide, please. There's the visible lava tube with a notable distortion, likely from the curvature, the surface combined with the lens and quality of the camera. There are also some points in the moon that seem elevated, similar to the first image. This image appears to be from the Lunar Orbiter Mission 5. The craters in the image have smoother edges, which would suggest that they're older impacts, and the lava tube under close inspection appears to be caved in, which leads us to believe that it's older as well. Next slide, please.
In this image, we have the lava tube highlighted in green with an arrow pointing to it just for further clarification. And we also have two of the larger impact points that we had noticed circled in red. We can tell that they're older due to the fact that they are fairly faint and
Gabrielle, you're muted.
Okay. There is a caved-in lava tube with a crater bordering it. Along this lava tube, there is a clear impact point present. This image appears to be taken near an area of raised land. Appearing mountains. This may have been caused by impacts pushing lava to the surface. The impact point in this image has very sharp and clear features, suggesting that it is fairly young in comparison to the two smaller craters upper left-hand corner of the image, which have softer edges. This photograph also is a part of the Lunar Orbiter Mission 5. Next slide, please.
You can see in the red mountain-like ranges and the blue arrow tube, and then circled in white the edges are, as you can tell. Next slide, please. And here's our image citation.
And that concludes our Moon 101 presentation. Thank you for the attention.
Okay, great, nice. Could you just go back to your first slide real quick? The one with the text, not your title slide. Okay, yeah. So the first thing I'll just say, in general, So you don't want to put up slides and then just read from them, because your audience could read it themselves. It's okay, like if you have this slide, for example, like in front of you, either printed or written out, and you can use those, that text to help you talk about an image, that's great. But I wouldn't put up a slide and just read from it. I mean, what you could do is just bring up the next image or the next slide. So go ahead and do that with the picture, and then talk about what you're seeing. I mean, that way people can actually see what you're talking about. It's kind of hard to, if it's a case where somebody has never seen this picture and you're talking about it, well, it's great, but it's a lot better if they can see it while you're talking about it. So that's just a general presentation tip. So question is, what did you do to decide that, or how did you decide these are craters, impact craters in this image?
Because they're circular and like it looks like where a crater has impacted, and the older ones and the younger ones.
Okay. So how do you know these aren't hills?
Because they're almost perfectly round.
Okay. Well, if you look down at orbital images of like volcanic mountains, for example, those are pretty round too.
I don't think the moon has volcanoes, does it?
No.
The moon don't have volcanoes.
Okay, no, that's fair. So these are all craters. You're correct. So the moon does have volcanoes. They're not like Mount St. Helens or Mount Fuji, type of real explosive volcanoes. It has more or less these mounds, volcanic mounds. So if you've ever seen like the mountains, and they're called cinder cones. If you ever seen those, like in northern Arizona, look up, when you have a chance, look up Sunset Crater National Monument. That's northern Arizona, and that's just there's a big volcanic field up in northern Arizona that has a bunch of these cinder cones. Volcanoes on the moon are like those. And they're not even like the Hawaiian Islands. That's even a different type of volcanism that formed those. But the moon does have volcanoes. They're not necessarily active. We don't have reason to believe they are, but there are what you think of as like a mound or rock, volcanoes. So the one piece of information I gave you, or let me ask you this, what piece of information do you think would have been helpful to kind of further solidify your idea that these were impact craters? There's a very important piece of information that you would need for any image you're looking at to help you discern what kind of features you're looking at. Any thoughts? So a very important thing to know when you're looking at an image is the direction and even the angle the sunlight's coming from, because sunlight produces shadows. So if you're looking, so in this particular instance, since these are craters, which they are, what direction do you think the sun is shining? Just in general, what direction do you think the sun is shining from in this image?
Direct, or maybe from the right side.
Okay, why do you think the right side?
Because on the crater impacts, you can see like the right side of it's lit, and the left side of it's more darker.
Okay. So what do we know about the structure of an impact crater? So yeah, there's a hole in the ground, but what else is a characteristic of an impact crater?
If they're big enough, whenever they impact, like whenever water drops, like water will come back up and then land in the middle. And if it's big enough, it'll create like rock to come up and then land back down. So there'll be like a pile of rock in the center of it.
Right, if it's large enough, exactly. But what about these small? These are all, so everything here in this image are simple craters. These are small, so then none of them are going to have that central peak. But what do all simple craters, assuming they're not really old, like the big ones that you circled there, what's a relatively new and fresh small impact or simple craters? What's a characteristic? What's one of their characteristics?
Defined edge.
Okay,
Like
so yeah, there's a very well defined edge. And what I'm trying to get at is the rims are raised. So compared to the ground or the surface around the crater,
Right.
their rims are raised. So if you were looking at this crater from the ground, it would look like mountains or hills in the distance. You wouldn't know there's a hole there necessarily. So where I'm going with this is, if the sunlight you were saying is coming from the left. So if the sunlight, are you saying the left or the right?
the sunlight's coming from the right side.
From the right. So if a sunlight's coming from the right side, where would you expect to see shadows in the crater if it has a raised rim?
On the right side.
Right. So where do you see the shadows?
On the left side.
Okay. So where do you suppose the light's coming from now?
On the left side.
Yeah. Light's coming in mostly basically from the left. Or think of it this way: if these were hills, let's just reverse our thinking. If these were hills, where would you say the sunlight's coming from?
From the right side.
From the right. Why is that?
Because the sunlight would be hitting the hill and it wouldn't be passing that point. Like the sunlight wouldn't create that divot and it'd hit the other side.
Right. It would just hit the side that's sticking up, that's in the sunlight. Right. So if these were hills, that would be the case, but craters, they're the opposite. And it's because they have that raised rim. Now, these bigger craters, especially the one on the right, those are older. So they've actually been filled in over time.
Yeah.
By other impacts throwing dirt into them. So they're not as deep. So and their rims are eroded away, basically. So there's not much of a hole left. Okay, good. Yeah, so these are all craters. The sunlight's coming from the left side of the image. And you can even kind of tell more or less how high the sun in the sky is. This certainly is not right overhead, but it's about maybe 45 degrees up, given the shadowing, maybe a little higher than that. I don't know if you noticed, but so the big crater on the right that you circled in red, did you notice anything on kind of what looks like would have been what's left of the rim? Did you notice anything other than smaller craters?
The bottom right side may be raised.
Okay, well, yeah, so there is a little bit of depth to this crater because there is some darkness there on the left side of it. But no, so what I want to point out to you is, do you see my cursor? Do you? Guess no, you don't. Okay. Okay, where you've got this circle up here, where you finish the circle, there's a little piece of red that kind of sticks away from the rest of the circle. You see what I'm talking about?
Yeah.
Okay, look just down below the end of that. Do you see that spot there?
Yep.
That is a spacecraft. That's the lander from the Apollo 12 mission. So this was the second mission that landed astronauts on the moon. And this is where they landed, right on the edge of this crater. And if you see those lines kind of extending away to the left of it, that's their footprints. That's where they were walking away from their lander and kicked up the dust and the regolith.
That is cool.
Behind their footprints. And if you follow it around the crater and then come back down towards the bottom and then towards the right side, you'll see more of their tracks.
Yeah.
And in that area there where it ends, that's where another unmanned spacecraft, I think it's Surveyor 6, landed a few years before. And they went over, or one of them, Alan Bean, went over to that spacecraft and took a piece off of it and brought it back with them. And then they were running some analysis on it to see kind of what, being in space like that for 2 or 3 years exposed to the sun and just the elements of space, what did that do to the material on that spacecraft? So anyway, I picked this picture for that specific reason. That's the Apollo 12 landing site. And I'd say about half the students catch that. Half the teams catch that there. They don't necessarily know what it is, but they catch that there's something there and they see these marks. So anyway, that's from Apollo 12. This image was taken by the Lunar Reconnaissance Orbiter, which has been up orbiting the moon since 2009. This picture itself, I think, is from like 2010. So it's actually a pretty old picture. Okay, so let's move on. Next picture. So you can skip the slide with the text, but the next one. So yeah, this is a lava tube, and it probably is a collapsed lava tube. You can tell because of, if you look on the edges, the slopes of it, particularly on the left-hand side where it's dark versus the right-hand side where it's lit up, you can see little boulders. So those are boulders that were probably part of the original roof that collapsed. If you come down towards the bottom where it's more kind of left and right, it looks like debris has fallen. It looks like there's a gouge in it. And what you guys circled, yeah, those are craters. And this is an instance where the sun is almost like straight overhead. There's not a lot of shadows, and that really kind of makes craters look weird. They don't look circular. But if you look at them in other images where the sunlight's lower, these craters definitely are circular. Okay, so let's go to the next one. Okay, so this is a great picture because there is all kinds of geology going on here, and you didn't necessarily use the terms, but you identify, well, you did in some cases, but you did identify everything going on here that I hope everybody would pick out. So this is a very complex geologic area. You can't see, but up here, so there's the rill that you called out, the lava tube. Near the top of it, where it kind of makes the elbow where this red line is crossed it right at the top of that, next to that mountain. Mm-hmm. You see what I'm talking about? Shelby, can you use your pointer real quick and move it to where I'm talking? Yeah, basically down a little bit. Yeah, right in there where that elbow, that bend in the rill is, just to the right of that is where the Apollo 15 astronauts landed. So this was in 1971, I believe. And this is a cool mission because you can find this on YouTube. There's a video of they took a falcon feather with them because a falcon was the name of their lander, and they do this experiment with a hammer and a feather, and they're like, okay, so Galileo basically said that in a vacuum, everything will fall at the same rate, no matter how much it weighs. So he stands and he holds a feather and a hammer, he drops them at the same time, and they both hit the ground at the same time because there's no air on the moon to slow down the feather. There's no air resistance from an atmosphere to slow the feather down, so they both hit the ground at the same time. So do a YouTube search for Apollo 15 hammer and feather experiment. It's pretty quick. It's like 20 or 30 seconds. It's pretty quick, but it's pretty cool. It's a really cool demonstration. So there's the rill. There's this is actually called Hadley Rill. The crater you circle is called Hadley Crater. Which happened first? Did the rill form first or did the crater form first?
The rill.
And how do you know?
You can see how the crater overlaps the rill.
Okay.
Yeah.
Very good. Very good. So the rill formed in this dark area. What do we call those dark areas on the moon like that?
Mare.
Yeah, it's Mare. This is the edge of, I believe it is Serenitatis Basin, Mare Serenitatis, where Apollo 15 landed. So this is part of that Mare. We got a rill, we got a crater, and we got all this bright white stuff. These are mountains. What do we call the brighter, higher points on the moon? What do we call those in general, collectively?
Highlands.
Those are the highlands, that's right. And in this case, these are highlands that were formed from when the impact created the basin. This is that rim where that rock gets pushed up. This is part of the rim of that very, very large crater. So in this, all the things we talked about in this picture, the Mare, Hadley Rill, Hadley Crater, and the highlands, how would you order, or which one of these geologic areas is the oldest?
The Mare, I would think.
Okay, DJ says Mare. What about you, Laura or Shelby? Gabriella, which one do you think is the oldest?
I think the highlands are the oldest.
Okay, Laura or Shelby, wanna?
I agree with Gabby saying that the highlands are the oldest.
Okay, Shelby, what do you think?
I also believe that the highlands are likely one of the oldest features.
Okay, DJ, tell me, why is the Mare oldest?
Because whenever the meteor hit the moon, it created the Mare, and it also created the highlands at the same time, but that was pushed up after the lava had filled it and pushed it out to the sides.
Okay. Gabriella, why do you think the highlands are the oldest?
Because of when the moon formed, it pushed the highlands out.
Okay. So this is all about timing of events, right? And understanding what formed on the moon first when it cooled. And the very first thing that formed on the moon when it cooled were the highlands. The very light, because as the moon cooled, the heavier stuff sunk to the interior of the moon, the lighter elements went to the surface. Those lighter elements include plagioclase, which is feldspar, which is what the highlands are made of. And when the moon's crust solidified, the surface solidified, that's what we had. The moon was entirely covered in this bright white rock. And over time, impacts came, formed these basins, interrupting that rock, that highland rock. The basins formed, and not right as they formed, but sometime later, lava seeped up through cracks in the basin floor and then filled in those low-lying areas with what we now call the Mare. So highlands are the oldest, then the Mare, then the Rill, and then the crater. Now that's all relative age dating, right? Just relative to each other. That's how old, that's their ages. But we don't have absolute ages, but those things are working on. We actually have a pretty good idea of how old Mare Serenitatis is. But that's another discussion. Okay. All right. Okay, go back to the other image real quick. The one right before this, the second image. Excuse me. Okay, this bend here in this rill, that's the same bend in that rill in the third picture. So this is a zoomed up image of that area that we saw in the last picture. So this is part of Hadley Rill. And the Apollo 15 site it's actually not, you can't see it in this picture, it's off to the right. But at Apollo 15, they had a rover. It was the first mission that had a rover. And they took this rover over here to the edge of the rill and actually took pictures. It's actually quite deep. So if you go look for Apollo 15 images of Hadley Rill, it's deep. It's not just a little ditch. It's pretty big. All right, very good, you all. Very good. You're off to a good start. You've got a pretty good understanding of some of this stuff so far. So one thing I would suggest just about presenting in general, I like how you mark things up, pointed things out. That's great. But leave off the text with the slides. You can use that text, but don't put it in your slides. It's much better to have an image to speak to. You could put text on slides, certainly, if there's something that it's going to help point something out specifically. That's fine. But the text you want to use to discuss the slide, don't put those on slides. But yeah, okay, let's do the asteroids. Starting to run out of time here. I could say more about these images, but I'm not going to. We need to move on to your asteroid presentation.
Next slide, please. We believe that this asteroid is one of the more younger ones because there's not a whole lot of regolith built up on it, and it's not very circular. You can see in the red circles, there's other smaller asteroids have been like attached to it through gravitational pull and them colliding with it. And where the blue arrows point to is where there's hardly been any impacts, or there's been so many that there's a large amount of regolith buildup. Next slide, please. No,
In this second image, we noticed that there were 3 main crater impacts in this asteroid image. And immediately above these 3 are another set of impact points, also 3. And the rest of the surface is dotted by smaller craters. This asteroid appears to be older due to the large impacts visible in the surface. And also the shape of this asteroid also gives us an idea of the age, as the older an asteroid is, the more spherical it appears. And over here in the yellow, it shows the impacts.
and you can also tell age by how much regolith is built up, and it's like a grainy top surface like the moon. Next slide, please.
In this image, you can tell that there is a lot of regolith buildup. And in the purple circles, we have rocks circled. And we can tell that this asteroid is older because of the regolith buildup.
That concludes the presentation.
It is.
Okay, good. Let's go ahead and go back to the first slide. Yeah, these these slides don't really take a whole lot of time to go through, because there just isn't as much geology on asteroids. Well, it depends on the size of the asteroid. In the case of this one, there's not a lot to talk about. This is asteroid Irkawa. This was an asteroid that was visited by a Japanese spacecraft that actually took samples of it and brought those samples back. So this asteroid could actually be 2 different asteroids that probably impact each other and wound up sticking, so to speak. So you can probably imagine where the 2 asteroids are. One of them is the kind of the horizontal piece. The other one is more of that angular piece. It's a thought that these are just a couple of asteroids that came together gravitationally. I don't recall the overall size of this asteroid, but I know the boulder on the right, I'm trying to think how big that is. It's I don't want to say, I don't want to guess because I would probably undershoot how big it actually is. But the fact that it's just sitting there perched on this thing, I mean, it's just like all the other large boulders, they're just bound gravitationally and rather weak gravitationally because these asteroids are not very big. And asteroids like this are what they call rubble piles that you probably read about, which means this whole thing is just a collection of very loose regolith and boulders. If a spacecraft were to try to go up to this thing and nudge it, it would have to be very careful about doing that, because if you put enough force on it, you could actually cause the particles to start separating, but then they'd probably just come right back together again. It's a really weird phenomenon, but it's gravity. That's how gravity works. There's a possibility that all of the particularly smaller particles are probably the electrostatic force holding them together, like static electricity that holds them together, is probably more powerful than the gravitational force keeping them together. But these are rubble piles that are just exactly that, piles of rubble. Okay, next slide, or next image, I should say. Okay, so this is part of the surface of the asteroid Vesta, which is, I don't think it's the largest, it's the second largest asteroid in the main asteroid belt. So it's mostly got, as you can see, craters, and at least what we can see in this image. There are other surfaces that have a lot more interesting things. But if you look between the two yellow circles that are on top, the top two, so to speak, the top left and the one on the right that you created, do you see what kind of looks like bands, almost like arcs or bands? So those are actually ripples in the surface of Vesta caused by a very large impact. So it's part of an impact crater that's actually kind of up and to the right of what's visible in this image. So that's actually what we call tectonics. This would be evidence of tectonics, just movement of the ground on Vesta. The triple crater feature there, it's actually called the snowman for obvious reasons, unless you've never seen a snowman. Which actually, if you said that in Arizona, depending on where you are in Arizona, some kids wouldn't know what that means.
I know
Honestly.
what that means, Mr. Shiner. It snows here.
No, I figured it does there. But I went to grad school in Arizona, and talking about Mars sometimes is nice because it looks very similar to Mars in the southern part of the state. But I grew up in Kansas, so you see a lot different weather there than you do in Arizona. So you got to be careful when you're talking to kids, different analogies you make, because they don't know what you're talking about. Okay. All right. And then finally, the last slide. So this one's a little deceiving because I didn't give you a kind of scale bar, but this is actually a very, very up close image of the asteroid Eros, E-R-O-S. I think for scale, like some of the largest boulders in here, like the size of a house, just to kind of give you a general idea. So yes, there's a lot of regolith on this, of course. But if you were to pull back and see the whole picture of the whole asteroid, it actually looks a lot like Irkawa, to be honest. But not as, it doesn't look as bouldery, I should say. But it is still similar in shape, a very similar shape. And you can see craters a lot more defined on Eros as well, impact craters. Okay, well, good job on both presentations.